Okay, so in the last lecture, right before this lab, we finished up our first problem of calculating the pH for a diprotic acid. Or actually, no, we did. I was a little further than that. And then we followed that up with the calculation of the pH of a weak base, ammonia. And that's where we left off. And so the next thing that we're going to talk about, or the last topic essentially in chapter 18, is figuring out the pH of a solution that contains ions. So some ions are acidic, some are basic, and some are neutral. So you'll need to be able to identify which are acidic, which are basic, and which are neutral. And this last part is all about identifying those in ionic compounds that are dissolved in water. So one thing to note is that, as we were pointing out with the bases, the stronger the weak base, the weaker its conjugate acid. And the weaker the weak base, the stronger its conjugate acid. These are related to one another, the strength of an acid and its conjugate base, or a base and its conjugate acid. For example, if we take a look at these two reactions here. So the first one is the ammonium ion behaving like an acid. So it is giving its proton to water. So it's behaving like an acid. So it loses the H and it loses the plus. Charge goes down by 1. And the H3O plus picks up the H. So now there's an extra H and it's positive. And so this would be the Ka reaction for ammonium ion. So ammonium ion is the conjugate acid of this weak base, ammonia, that we were just talking about in the previous problem. If the ammonia is acting like a base, it will take a proton from water, and thus it will have an extra H, 4 H's instead of 3, and the charge will go up by 1 unit from 0 up to positive 1. And the H plus came from the water, so you can see there's only 1 H now, and the charge goes down by 1 from 0 down to negative 1. And if we add these two reactions together, what we will see is that ammonia here is on this side, and it's also on this side, so it would cancel. And ammonium is on this side, and ammonium ion is on this side. So what we get when we add these two reactions is 2 waters right here, 2 waters, and a hydronium ion and a hydroxide ion. This is just the equation for the autoionization of water. So we know the K for that reaction, that's what Kw is. The K for this reaction is defined as Kw, K for water. So remember that if we add two reactions, to get the K, we multiply these two reactions to get this K here. This is because if we were to write the Ka expression for the first reaction, well, it would be hydronium ion times ammonia ion concentration over ammonium ion concentration. That's the Ka expression for this reaction. If we were writing the Kb expression for the second reaction here, it would be the products, ammonium and hydroxide ions to the first power, their concentrations, over reactants, ammonia. And again, we can see if we multiply these two Ks, that gives us the K at the end, because the ammonia cancels, the ammonium cancels, and we get hydronium times hydroxide, which is Kw. So the point is that the Ka, or the Kb for a base, and the Ka for its conjugate acid, those Ks multiply to Kw. If we were to look up on the previous slide, there was a slide full of Kb's and Ka for the conjugate acid. This was the Ka for, this was the Ka for ammonium ion from that chart. And this was the Kb for ammonia from that chart. And of course, they multiply to 1 times 10 to the minus 4. So often, the reason why we need to know this is that often when we look at the appendix in the back of the book, And I have a copy of the appendix I'll be posting up right after this with KAs in it and KBs, but you also have your book with the appendices and they're online as well. But the KBs for bases are generally given, but the Ka for their conjugate acids, such as ammonia, is not given. So KBs are only given for neutral bases, and Kas are only given for neutral acids in the chart. The Ka for ammonium ion is not neutral, so its Ka is not given. You have to figure it out from the Kb. So since Ka times Kb for a base and its conjugate acid or an acid and its conjugate base also is multiplied to Kw, we can figure out the K for a ion such as ammonium from the Kb for the neutral base that it is the conjugate acid of. Did anyone want me to go over a part of this concept again? So again, in your appendix, KBs for neutral bases are given. KAs for neutral acids are given. But Kas and Kbs for ions are not given, such as ammonium ion. You have to figure them out from another K. And so, in general, since the Ka and the times the Kb for a conjugate acid base pair multiplied to Kw, if you have, which is at 25 Celsius, it's this is the value. If you want the Ka for an ion and you have the Kb for its conjugate base, you just do Kw over the Kb. That will get you the Ka for the ion, which is the conjugate acid of a particular base. If you want the Kb for a base that is a conjugate base of a neutral acid, you'll do Kw over the Ka for that neutral acid. Again, you can look up Kbs for neutral bases and use those to determine the Ka for this conjugate acid, which would be an ion. And you can look up the Ka for a neutral acid and use that to find the Kb for its conjugate base, which would be a negative ion. Also, pKa plus pKb add up to pKw, which is 14. Likewise, pH and pOH add up to 14 as well. So those are useful shortcuts that you can use if you like. You don't need them because there are other ways that I showed you to get, pH and pOH and so forth. But the point is that to get the Ks for ions, which are the conjugate acid of a base or the conjugate base of an acid, we will need to look up the Ks for the neutral acid or conjugate base and use those to figure out the K. So, as you saw, just going back, ammonium ion in the last example here, this was an acid. Ammonium ion is acidic. So what we want to be able to determine is which ions are acidic and which ones are basic. And so, for example, sodium chloride solution contains sodium and chloride ions. Sodium and chloride ions are neither acidic nor basic. So they produce a solution that is pH 7, which is given by this universal indicator here. This is like the red cabbage juice indicator that you found out about in the experiment 8. Ammonium ions are acidic, as we saw before. So chloride ions are neutral, but ammonium ions are acidic. So this solution with ammonium ions in it has a pH less than 7. Small, highly charged positive ions are also acidic. So aluminum, for example, as we'll see, is a very small, very highly positively charged ion. And for reasons that we'll talk about, these produce acidic solutions. And so you can see this solution of aluminum chloride is acidic. Its pH is less than 7. So sodium ions, again, as we saw here in the sodium chloride, sodium +1 ions are neutral for reasons we'll talk about. Cyanide ions, however, are basic. So if you have cyanide ions in solution, you get a solution that has a pH which is greater than 7. Now, sometimes you could have a mixture of acidic positive ions, for example, ammonium ions are acidic, as we saw right here, and basic negative ions, such as carbonate. And to determine whether the solution overall would be acidic or basic, we would have to compare the Ka of the acidic cation to the Kb of the basic anion and see which one is bigger. That's what would tell us if the solution is acidic or basic. Now, there is a kind of recipe to figuring this out. What you could do, this is why I teach my Chem 101 students. I think you guys should have a deeper understanding. But what you can do is you can look at the acid that would be composed from the anion and the base that would be composed from the cation. And if the acid and the base that neutralized each other made this salt, and they're a strong acid and a strong base, the salt made from their neutralization would be a neutral salt. If you have a salt that could be made from the neutralization of a strong acid and a weak base, that salt would be an acidic salt. It would make an acidic solution. I'll show you some examples too. If you had a salt that could be made from the neutralization of a weak acid and a strong base, this would make a basic salt. And for reasons we'll talk about, let's look at the examples. So let's look at some examples here. So salts that yield neutral solutions, they would contain the cation from a strong base. So these include all of the group 1 cations. Essentially, these are just spectators. It's pretty useful to remember that in general, group 1 cations, positive ions, don't really tend to do a whole lot in solution. They're just happy to be there. These would be the cations from a strong base, such as lithium hydroxide, sodium hydroxide, and potassium hydroxide. These could also include alkaline earth metals. So this is calcium, strontium, barium, not beryllium though. And then in salts that have neutral solutions would contain the anions from strong monoprotic acids, such as chloride, bromide, iodide, nitrate, and perchlorate. All of this has to do, so as I said, if you had a base that was formed, that was a strong base, basically, a salt that was formed from a cation from a strong base, these guys here, and a salt, and also from an acid that its anion is, or an acid, the anion is from an acid that is a strong acid, such as HCl, HBr, HI, and so forth. These would make salts that are neutral. And here is the reason why. These cations from the strong bases don't tend to react with water in any way. And so they do not behave as bases. You can remember them as being the cations from the strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium, strontium, barium hydroxide. Those are all strong bases. The anions from monoprotic acids, well, let's think. For an acid to be strong, that means it completely separates from its protons, which means that these ions would be completely separated from any available protons, and they would not want to go and grab any protons. They are the conjugate bases of strong acids. So basically, these are terrible bases. They're not bases at all. Basically, the stronger the acid, the weaker the conjugate base, right? So we can see here, these are not bases really to any great degree. So if your salt contains these cations and these anions, it will make a neutral salt. None of these positive ions will act like a base, and none of these negative ions, none of these positive ions will act like an acid, and none of these negative ions will act like a base. And in general, it takes a positive ion, or rather, it takes a negative ion here to act like a base, right? If it's an ion, so it can grab a proton, because that's what bases do. So yeah. So these would not work as act as bases. These would not act as acids. Again, don't memorize these. Think about these in terms of the base that they would be associated with. These positive ions are associated with strong bases. These negative ions are associated with strong acids. They're the conjugate bases of strong acids. Now, salts that contain the conjugate acid of a weak base, such as the weak base ammonia, its conjugate acid is ammonium ion. That's what you get when you add an H plus to it. The weaker the base, the stronger the conjugate acid. And so conjugate acids of a weak base will behave as decent acids. As you can see here, ammonium ion can give its proton to water, make hydronium and hydroxide. So let's say you have salts like ammonium chloride. Well, as we saw in the last slide, the chloride ion is the conjugate base of a strong acid, so it is not acidic or basic. But the ammonium ion is the conjugate acid of a weak base, and so it will behave as an acid. So the conjugate acid, so cations are the conjugate acids of a weak base, can behave like an acid. So ammonium chloride here, we saw that this was acidic when dissolved because the chloride is neutral, but the ammonium is acidic since it is the conjugate acid of a weak base. There are other cations that can make acidic solutions. They are small, highly charged cations. So we're talking about elements that are in the first 4 rows of the periodic table near the top, particularly those that are very high in charge. The best example is aluminum positive 3. So if we look at the periodic table for aluminum, we will see that aluminum is near the top. It's quite small. It's in the 3rd row, and it has a positive 3 charge. So it is a small and highly charged cation. If you had iron 3 plus or manganese, or let's say chromium 6 plus, these would also be small, highly charged cations. Nothing below row 4 would really be considered small. So we're talking about small and with a charge that's like 3, probably 3 plus at least, with the exception of beryllium. Beryllium, if it's positive 2 because it's so small, that would be enough to be small and highly charged. Here's why cations that are small and highly charged make acids. It's because these transition metals make a transition metal complex with water, as we had seen before. So here, aluminum is the transition metal, and water is the ligand, and there are 6 ligands surrounding, 6 water ligands surrounding it in an octahedral arrangement. So this makes the hexaaqua aluminum ion. Now, when this happens, this hexaaqua aluminum ion actually is because the cation is small and highly charged, it is pulling electrons inwards towards itself. The result is an inductive effect like we saw early in the chapter, which weakens the bonds between the oxygen and the hydrogen here. So it's quite easy for one of these H pluses to pop off, and then you get an acid. So here, this H plus that was there, it's no longer there. It's now stuck to the water. And so the result is that this hydrated aluminum cation behaved like an acid. One of the water molecules released a proton. This only happens for small, highly charged metal cations. The best examples would be beryllium and aluminum. So lithium, for example, which is right next to beryllium on the periodic table, not acidic at all. Also, sodium and magnesium, not acidic. But beryllium is small, it is highly charged, it is acidic. Aluminum, small and highly charged, it is acidic. Generally, if it's in the first 4 rows of the periodic table and it has a charge of 3 or greater, it may be acidic. Beryllium is an exception. It's so small that positive 2 makes it acidic. So the acidity of a hydrated metal group kind of increases from left to right on the periodic table as the charge increases, and also as the metal ion size decreases. So near the top and the right side of the periodic table, those metals are the acidic cations. Like aluminum is the best example. It's the most acidic, one of the most acidic. Now for salts that yield basic solutions. So you're going to have a base. The base will come from the negative ion. So for example, if you have sodium cyanide, we already decided sodium is part of the strong acid as a part of the base would be the cation that's part of sodium hydroxide, strong base. It's not going to be acidic nor neutral. But cyanide ion is the conjugate base of the weak acid cyanide. So hydrocyanic acid rather. HCN is a weak acid, which means some of it will give up its proton, but some of it will stay with the proton. That means cyanide ions, because HCN is a weak acid and hangs on to its protons to some extent, cyanide ion, its conjugate base, is willing to grab some protons and behave like a base. So here is the equation written for cyanide ion acting like a base. The H plus moves from the water. The water is acting like the acid right now. The cyanide is the base. The H plus goes over to the HCN and it gets H plus, so the charge moves up by 1 unit from -1 to 0. And the water gave the proton. It was the acid, so the H goes down by 1 and the charge goes down by 1 unit from 0 down to -1. So negative ions that are the conjugate base of weak acids will make basic solutions. They will be basic. And so that's how you evaluate whether a salt solution will be acidic or basic or neutral. What if this salt contains, but before I go on, that's more complicated. Jane will want me to go over a part again about ions that make a neutral or an acidic or a basic solution. So just a quick rundown. Acidic solution, again, acidic solution will be from conjugate acid of a weak base, a cation that's a conjugate acid of the weak base, or a small highly charged cation. Basic solutions will come from negative ions that are the conjugate base of a weak acid. Otherwise, the solution is neutral. Now, what if you've got a salt that contains both? So ammonium ion is the conjugate acid of the weak base ammonia. And carbonate ion is the conjugate base of the very weak acid, bicarbonate ion. So if we have both an acidic cation and a basic anion, a basic negative ion, how will we know if the solution is acidic or basic? Well, what we want to do is compare the Ka for the acid to the Kb for the base. If the Ka has a higher Ka than the Kb for the base, the solution will be acidic. But if the Kb for the base is larger than the Ka for the acid, then the solution will be basic. Let's calculate this real quick from some numbers we've seen before. So again, ammonium ion will behave like an acid because it is the conjugate acid of the weak base ammonia. So it will give its proton, make H3O plus, and we'll be left behind with ammonia, its conjugate base. The carbonate ion is a base because it is the conjugate base of the very weak acid HCO3 minus. And so it would behave like the base. The H plus would come from the water. So we'd add an H and the charge would go up by 1 unit from -2 to -1. And what would be left of the water is 1 oxygen, 1 hydrogen, and the charge, since it lost H+, the charge would be down by 1 unit from 0 down to -1. What we want to do here is compare the Ka for ammonium ion to the Kb for carbonate ion. If the Ka is greater than Kb, the solution will be acidic. If the Ka is less than the Kb, the solution will be basic. If Ka and Kb are about the same, the solution will be close to neutral. So remember, we cannot calculate the Ka directly, or we cannot, read from the book the Ka directly from the book, because this is an ion. What we instead have to do is look for the Kb of the neutral base, and then we can use its Kb to find the Ka. Likewise, we're not going to have a Kb for carbonate ion. What we need to do is find the Ka for bicarbonate, and this is actually the Ka2 of carbonic acid. And so the Ka for ammonium ion is going to be Kw over the Kb for ammonia. And what I want to do now is show you where we'd get the Kb for ammonia. So this is from your book. I'll post this as a kind of shortcut so you don't have to look in your book if you don't want to. I forgot to post it this morning. But if we go here, I do have PDF, which I'll put up there. There we go, 8th edition appendices of the, I have thermodynamics and, I thought I had the equilibrium constants too. Well, if you go in your textbook anyway, you might as well just use the textbook since in case you might have it. I'll give you just a copy of I'll give you a copy rather of the appendices themselves. But if you go in the appendices, page A8, you'll get the Kas for a variety of acids here. So we're looking for carbonic acid, and we want the Ka2 of that because that would be the Ka of the bicarbonate ion. So it's 4.7 times 10 to the minus 11. And then for Kb, the Kb's come after that. And again, you'll see for all these weak bases, they tend to have nitrogen atoms in them, which are highlighted in blue. We're looking for the Kb of ammonia. It's 1.76 or 1.8 times 10 to the minus 5. So if we want to find the Ka for NH4 plus, we're going to put Kw over the Kb, which we found to be 1.8 times 10 to the minus 5. So that gives us the Ka for ammonium ion. Let's put that in the calculator. I want to remind you guys, you do have to use your EE or EXP here on both of these, otherwise you won't get it right. You should calculate with me if you can. 1 EE negative 14 divide, here's where you have to use your EE, make sure you use it, 1.8 EE negative 5. And we get 5.6 times 10 to the minus 10, or the Ka for ammonium ion. We do Kw over the Kb for its neutral conjugate base. Then Kb for bicarbonate ion, carbonate ion will be Kw over the Ka for bicarbonate ion, which is Ka2 for carbonic acid. If carbonic acid lost 1 proton, it makes bicarbonate ion. So this is when it loses a second. And so we looked that up from the appendix. It was 5.6 times 10 to the minus 11. And then we divide those again, 1 EE negative 14 divide 5.6 EE negative 11. And we get 1.8 times 10 to the minus 4. So since the Kb for carbonate ion is greater than the Ka for ammonium ion, this solution will be basic. So did anyone want to ask a question about that example there? Okay, so the hardest part for this is recognizing that the Ka for HCO3 minus is the Ka2 of carbonic acid. Again, you can tell because this is not neutral itself. If it had one more proton, it would be H2CO3, it would be neutral. So this is indicating the loss of a second proton from a neutral acid. So that's why you need to go and get the Ka2 for carbonic acid. That is the Ka for bicarbonate ion. So in summary, if you have cation from strong base, anion from strong acid, such as these guys, the solution will be neutral. The cation will not be basic, the anion will not be acidic. If you have a cation from a weak base and an anion from a strong acid, the cation from the weak base, it is the conjugate base of a weak acid, so it will be acidic and will cause the solution to be acidic. The anion from the strong acid will be neutral because strong acids separate from protons, so their conjugate base does not want to grab protons. If you have a small, highly charged cation, that will make an acidic solution. If you have a cation from a strong base, well, that will not do anything, like sodium, potassium, lithium. It will just be a spectator. That's something to really, really keep in mind. These sodiums, potassium, all these are just spectators. They're not going to be involved. They're not going to be acidic or basic. And the anion from a weak acid will be basic. So the conjugate base of a weak acid is basic. The weaker the acid, the stronger the conjugate base. And if you have both, well, then it's difficult to know if you've got an acidic or basic solution. You'll have to figure out the Ka of the acid ion and the Kb of the basic negative ion to figure out if the solution is acidic or basic. So in addition, you can calculate the pH of a solution that has a salt. So in the previous examples, we were just calculating the pH of a solution that had a neutral weak acid or a neutral weak base in it. But we can also calculate the solution for the pH of a solution of a salt here. So our salt is ammonium chloride. So what we have to do is first analyze the salt and see, is the cation acidic? It is, because NH4 plus is the conjugate acid of the weak base ammonia. So this cation is acidic. Chloride ion is the conjugate base of the strong acid HCl. It is not acidic or basic. It stays separate from its protons because it's the conjugate base of a strong acid. So it's a very terrible base. It's not a base at all. So we're going to focus on the ammonium ion because that's the part that's going to affect the pH. It's acidic. Now, as we saw in the previous slide here, the Ka for ammonium ion, we determined it from the Kb for ammonia. It's 5.6 times 10 to the minus 10. So I'm going to use that in the problem. So we write the equation for ammonium acting like an acid. So ammonium is acidic because it's the conjugate acid of a weak base. Chloride is neutral because it's the conjugate base of a strong acid. So on our reactant side, it's going to be our acid, ammonium ion, and water. There's going to be an equilibrium, and our acid here will give the proton to water. So we will get the conjugate base of that acid, ammonia. So we lost the H, charge went down by 1 unit. And the water gained an H and H plus, the charge went up by 1 unit. So like all these where we have to determine the pH at equilibrium, we're going to have to make an ice table. So we make the ice table, And our ammonium chloride is 0.5 molars. So that means when it separates, it's going to make 0.5 molars of ammonium ions and 0.5 molars of chloride ions, since there's one of each. So our ammonium ion concentration is going to be 0.5 molar. We're going to start with no ammonia and about 0 molars of hydronium. Of course, there's a little bit always in water, but we're going to consider it negligible. And next, since there's no products, this reaction can't go backwards, it must go forwards. So we're going to put a minus x here, minus 1x, since there's a 1, plus x here, plus 1x, and plus x here. So our equilibrium concentrations for ammonia will be 0.5 molar minus x, and for ammonium, it will be x, and for hydronium, it will also be x. So now let's write the K for this reaction, which is the Ka of ammonium ion. We're going to put ammonia and hydronium on the top. So we put ammonia, hydronium, each to the first power, since there's ones here. And on the bottom will be ammonium ion, also to the first power, its concentration. And so now we can plug these in. X is the equilibrium concentration for ammonia and hydronium, X and X, and 0.5 minus X is the equilibrium concentration for ammonium ion. Okay, and so we're going to take this now and take this to the next slide. Also, by the way, this is the Ka, so the value for Ka, which we had already gotten, was 5.6 times 10 to the minus 10. So let's take this down now to the next slide. So the Ka, going back again, was x times x over 0.5 minus x equals 5.6 times 10 to the minus 10. Now we should check to see, can we use our simplifying assumption? Will this x be small enough that if we subtract it from 0.5, it won't make much of a difference? So we're going to take our initial concentration and divide it by our K and make sure that it's greater than 400. It is. So we can go ahead and assume 0.5 minus x is about the same as 0.5. So we're going to put x, leave the x's on the top, but this is going to be now 0.5 instead of 0.5 minus x. So now let's copy this down. We're going to put x squared now on the top, x times x, and 0.5 on the bottom. And that is equal to our Ka, which was 5.6 times 10 to the minus 10. Now we're going to multiply both sides by 0.5. So I'll write that in here. So we'll do times 0.5 times 0.50. And these will cancel here, and so we'll get x squared on this side. And we've got to multiply this, so let's do that. So 0.5 times 5.6 e minus 10. And we get 2.8 times 10 to the minus 10. Okay. And so let's continue now. So we'll have x squared on this side times 2.8 times 10, or equals 2.8 times 10 to the minus 10. Now we have to square root both sides. Square root. Okay, so let's take the square root of that in our calculator. So we'll have to the power of 0.5, that's square root. And we get 1.7 to 2 sig figs, 1.7 times 10 to the minus 5. And so that's next here, and that is the hydronium concentration. So all we need to do now to find the pH is take the negative log of that. So the negative log of 1.7 times 10 to the minus 5. So we do 1.7 times 10 to the minus 5. We'll take the log, change the sign, and we get 4.77. Remember, since this has two sig figs, the 1.7, we need to write our answer 2 after the decimal. So 4.77 is our result. And so that is how you calculate the pH of a salt solution. Remember, you'll have to get the Ka for your acid ion from the Kb for the neutral conjugate base, or the Kb for your negative basic ion from the Ka for its conjugate acid. Anyone want me to go back and talk about a step or two here? Okay. So for this chapter, you should be able to figure out the pH of a strong acid solution, a strong base solution, a weak acid solution, a weak base solution, or a solution containing a salt that has an acidic or a basic cation, or acidic cation or basic anion. I will not have you calculate pH for mixtures of acidic cations and basic anions. That's just too complicated. Okay, that's a really advanced thing to calculate. We don't do that in this class. Another way of talking about acid base is with this extremely broad definition. So at the beginning of the chapter, we gave you the most common definitions. One, which was Arrhenius. Arrhenius' definition was that an acid is anything that makes H+, and a base is anything that makes OH-. Then Bronsted-Lowry was a little bit more broad. It said an acid is anything that makes H+ in water, but a base is anything that accepts H+, which could be hydroxide, or it could be something else that acts like a base, like ammonia. The most broad definition of acid base is the Lewis definition of acid base. I had a teacher in UCR, he made superacids, and he liked to try to describe almost every reaction as an acid-base reaction. He was really obsessed with that. And Lewis acid and base does extend the idea of acid and base very, very broadly. The way it works is that if you have a molecule donating a lone pair in order to make a coordinate covalent bond, the way ligands do from chapter 23, we say that that is the base. It's the electron pair donor. And the acid is the acceptor of the electron pair. So in the case of like chapter 23, it would be the transition metal ions acting as a Lewis acid. And the reason why this definition works is because, remember, when we had these small highly charged cations that attach to water in this fashion, they make acids. And so this ends up being the broadest definition. It even applies to H+ and OH-. OH- is the electron pair donor, hydroxide. The oxygen has the electron pair it gives, and the H+ is the electron pair acceptor. It has no electrons, but it accepts the 2 electrons to make the bond. So this is the broadest definition of acid and base, Lewis acid and base. So you can see the way in which this works here. So this applies very generally because the bases generally behave like bases and accept a proton because they have a lone pair like the one on nitrogen here to accept the proton. And so in a molecule that will donate a lone pair, it could donate it to H+, but it could donate it to something else too, such as a transition metal cation. So just the act of it donating the lone pair makes us consider it a base, because it could have donated that to H+ and accepted an H+, but instead it's donating the lone pair to something else, but the results are generally the same. This solution becomes less basic because it doesn't have any free ammonia anymore, which is a base. And so we can see that here, when we add we have a copper solution, just pure copper ions. We add ammonia, and it makes it first to precipitate copper 2 hydroxide, because the solution was basically had hydroxide in it. We add some more, and we get a transition metal complex with ammonia. But basically, ammonia is acting like a Lewis base because it's donating an electron pair to make a bond. The copper is acting like a Lewis acid because it is accepting the lone pair to make that bond. And you use this kind of trick sometimes when you were doing your qualitative analysis too, in experiment 13, to precipitate out some things. Here's the most common example from the environment. There are various pollutant molecules that behave as Lewis acids. They will accept an electron pair from water in order to create an acid. One example of this is sulfur trioxide. So this is often produced when coal is being burned. It can accept a lone pair from oxygen, and then the bond rearranges so that the oxygen here bonds to the hydrogen, and what you get is sulfuric acid. So the result is an acid is produced because this sulfur trioxide can accept the lone pair from water. And all of these gases, these other gases do it as well. NO2, SO2, CO2, these can all react with water in this fashion and make acids. And so that is why pollution often leads to acid rain. You may have heard of acid rain before. It was a big problem, particularly in highly coal-built cities like London back in the late 1800s, or some of China, even more recently than that, where there's a lot of burning happening. You get a lot of reaction of these pollutant molecules with water, and they produce acids, which leads to acid rain, which then goes into the ponds and lakes and kills wildlife, and also does damage to rocks and structural materials and stuff like that. Okay, and that is the end of chapter 18. So before I move on to briefly introducing chapter 19, did anyone want me to go back and talk about one of the previous concepts, such as why a cation might be acidic, or an anion might be basic, or Lewis acid base parts, any of that? Okay, so that's the end of chapter 18. You should be well underway on your chapter 18. Whoops, I stopped sharing my screen. Share screen. Oh, I'm sharing. What am I sharing now? I didn't stop sharing the screen. I closed my full screen projected screen. Okay, there we go. Okay, so, all right. So let's open up the chapter 19 slides briefly. Today, your goal in your experiment is going to be to see what happens when you mix acids and bases together. What happens to the pH? So, what you're going to be doing is you're going to be doing a virtual experiment where you're going to be mixing a strong acid with a strong base, which gives you a neutral solution when they're mixed in the exact same amounts. You'll be mixing a weak acid with a strong base. You'll actually be doing this one, I believe, acetic acid with sodium hydroxide. It will produce water and sodium. So notice here in all these, I'll go over these in a little bit more detail, but basically the way a neutralization works, you probably learned this in your previous class. The H plus goes with the OH minus, it makes water. And then the positive ion sodium here goes with the negative ion chloride, it makes sodium chloride. And that's the neutralization. And of course, this is a neutral salt, as we just learned. The positive sodium ion and the negative chloride ion, which is the conjugate base of a strong acid. You'll mix a weak acid with a strong base. This one in particular here, again, this weak acid, H plus here, reacts with OH minus, and you get water. And then the salt is made from the sodium positive 1 ion and the acetate negative 1 ion, sodium acetate. And because acetate is the conjugate base of a weak acid, it will behave as a base and make the solution basic when they're equivalent here. You'll also mix strong acid with weak base, this one in particular right here. Here the acid H will give its H plus to the weak base. And so you get NH4 plus, and the negative ion is chloride. So you get ammonium chloride, which is acidic. This one looks a little bit different from the others because the base does not contain hydroxide here. It contains ammonia. So that's what's grabbing the proton. Finally, you'll also mix a weak acid with a weak base and see what happens to the pH when you do that. You'll mix ammonia and acetic acid. And here the H plus is given to the ammonia. You get ammonium ion and H4 plus. And the rest is acetate ion. And the pH is question mark. Well, it depends on the relative strengths of the acid and the base. So specifically, what you're going to be doing here today is a titration. So a titration is basically a very careful mixing of two substances. We're doing an acid-base titration, so it's going to be a very careful mixing of an acid and a base. And we're not going to find an unknown concentration. Instead, what we're going to do is we're going to just watch the pH as we mix them bit by bit. You hold a certain standard solution that you know the concentration of in the burette. Often in the Erlenmeyer flask here, you have a solution of unknown concentration. In our experiment today, will be known. And you'll see the pH change in this fashion. So what you're going to see, and you'll see this in the way I have the data sheet set up, at first the pH will not change much until you have close to the same amount of base and acid. So here, this is showing sodium hydroxide being mixed with HCl. And you can see that as you're adding sodium hydroxide, the pH is going up, it's getting more basic. But when you get to having the same amount of base, the same number of moles of base as you have acid, the pH starts to rise quickly. And the equivalence point is the point where you have equal moles of acid or base. So since we're using, in this case, the same concentration, sodium hydroxide and HCl, we have 40 milliliters of the HCl. When we add 40 milliliters of sodium hydroxide, that's when we're going to get to the equivalence point. And since this is a strong acid, strong base titration, and it's going to produce the salt sodium chloride, a neutral salt, at the equivalence point, the pH will be 7. So today you're going to actually observe where the equivalence points are yourself. So you're going to take a look at where the equivalence point is. This will be once the pH has risen. You can see it from the graph here. The way you identify it is you'll see it right there at the middle of the sharp rise. That's where the equivalence point is. And you'll be able to figure out the pH. So you're going to do, there are 3 types of titrations that we're going to do calculations for. You're also going to do a titration for a weak acid, weak base today, but we're not going to calculate pH. We're just going to read it. And so I'll teach you how to calculate the pHs for those. But today you don't need to do the calculations. Let's look at our experiment for today. Our experiment is going to be experiment 10. Now for experiment 10, I want you to look on canvas. So I'm going to show you on canvas where this stuff is. So on canvas here, I have put in a lab assignment under assignments, experiment 10. And so here are the instructions. Download the experiment 10 online version, and there's an Excel file that you can fill in. So you'll fill in this Excel file. This will allow you to make a graph. You could also copy this into Google Sheets if you like. I posted the files this to avoid having too much clutter in the module. I just left the files in the files folder. I'll show you where that is. You'll read the assignment, do the pre-lab, and then we're going to perform the virtual experiment using Chem Collective, and you'll enter your data into the Excel file and use that to make a graph. You're going to do 4 titrations and enter all the data into the same Excel worksheet. And you'll fill it in. And then for the report sheet, you can either type directly into it in Word or you can fill it in by hand. But the Excel one, you should use your computer. And and then when you finish with the Excel file, in order for me to see everything, make sure you turn it into a PDF, and I'll show you how to do that. So if we go to Files here, you're going to see lab documents. And I already have all the lab documents up. I've had them up for a little while. These are the lab documents for Experiment 10. So there's a Word document here and an Excel document. So I'm going to open the Word document first. So here's the Word document. And what you're going to be doing is following this procedure. It's very much like your procedure in your lab manual, the one you had paper. The difference is the concentrations of each of these. I chose 1 molar because that's what was all available on the Chem Collective virtual lab. I think in the original experiment it was 0.1 molar. Yeah, but I changed all the 0.1 molars to 1 molar in here. Oops, not this one. Uh-oh. It should have been 1 molar. Everything's 1 molar, not 0.1 molar. I did miss one there. I missed a couple. So note that everything's going to be 1 molar. You're going to use a 1 molar, okay? And I'll try to fix that. You're going to go to the Chem Collective virtual lab, this one in particular, and we're not going to do exactly the assignment that they told you to do, the unknown acid base. We're going to use the known ones to make it more like our experiment. Again, if you are having trouble using this, there's a video here, introductory video. You can watch this again, and it shows you everything that I'm going to show you here, but I'm also going to show you. So for example, in your first titration, you're going to be using 1 molar HCl and 1 molar NaOH. So we'll want to grab those in the stockroom. So we'll look for strong bases NaOH, and we'll grab the 1 molar NaOH. And then we'll also go back to the stockroom solutions, and we'll go to strong acids, and we'll look for the 1 molar HCl. So there's various concentrations here. We want the 1 molar. So now we have the 1 molar NaOH and the 1 molar HCl. Okay. And then, so on the procedure, it says we're going to obtain a burette. And with a real burette, you would rinse it with, you know, a few milliliters of NaOH. Of course, our burette will come to us perfectly clean, so we don't necessarily need to do that here. So to get the burette, you go to glassware, and you'll go to other and get a burette. So there's our burette right there. Okay. So it says, oh yeah, I should have gone step 2 here. So step 2, we're going to place 8 milliliters of HCl solution into a 250 milliliter beaker. So we'll go to the stockroom again, go to glassware, and go to beakers, and we'll get a 250 milliliter beaker. Now, if you were really doing this experiment, you would want to measure this exactly. And I think you should do this just to remind yourself. So we're going to be putting, actually, I think I can half screen this right here so that I can show this in the other half. Okay. So now to transfer 8 milliliters, you can just drag this over the beaker. I should show a bit more. And you can do precise, and if you click 8, it will pour 8.000 milliliters. Okay, you can do that. Although you couldn't actually measure with that precision with just pouring it in this way in real life. So what you may want to do instead, so I right-clicked this and chose to remove liquid. What I think you should do, just to remind yourself of what you would do in the real lab, is you would go and get a pipette. And you would put I guess they have disposable pipettes here. They don't have an 8 milliliter pipette. They don't have a 1 milliliter pipette. I guess, so what you're going to have to do is just do it this way. So put it over. Just remember, you would use a pipette to transfer this in real life. And you can hit 8 here, and it will pour 8.000 milliliters. So that's our HCl. We can now remove this. We're not going to need more HCl for this one. What we do want to do is we want to add 100 milliliters of distilled water. So if you go to solutions, distilled water is right here. Again, drag it over, and we'll put in 100 milliliters. Pour. And now I'm going to remove this, but one thing that I think you should do while you're doing this too is you should grab one of these pure waters and just leave it here, so you have a reference color for clear, because your solution is going to turn pink, and without a reference color for clear, it can be hard to tell that it turned pink. And the reason why it's going to turn pink is we're going to add phenolphthalein. So we go back to the stockroom and we go to indicators, and there's a variety of indicators. We're going to use phenolphthalein for this experiment. And it says to put 3 drops, 0.5 milliliters. So you can just drag it over and put 0.5 milliliters, pour. And so now your phenolphthalein is in the solution. We can remove that. Okay. And so again, we're going to keep this water here so we can compare the color. Next, we want to put 50 milliliters of NaOH into the burette. I'm going to show you something about the way this burette works here. So I'm going to drag it over, and you can see it here. If I put 50 milliliters, 50, pour, you're going to see that it only goes up to the 2 milliliter mark. It's because some of this had to be used to fill up the tip, and that's not measured on the scale. So if you wanted to start at 0.00, which is fine, put another 2 milliliters in there and put pour, and now you're starting at 0.00. So now I can remove my NaOH, and I can begin to titrate my solution, my acid here. The way I'll do that is I'll grab the burette and I'll drag it over. Now, let's open up the Excel document at this point. And this is where, so I said, yeah, drag the burette over, and then you're going to want to add things slowly at first. And I tell you how many increments to do, or what measure of increments to do. It's also on the Excel file here. So what you would do is you would open this Excel file, and we'd first get the pH with 0 milliliters of titrant delivered. So to get that, we can click on the beaker, and it will tell us the pH right over here in the corner. So the pH of this, of what we have in the beaker to begin with, is 1.13. And then we're going to add 1 milliliter. So I'll drag it over again, and right now it's showing the pH inside the burette, which is 14, but as soon as you deliver some, so we'll deliver 1 milliliter, it will switch to showing the pH in the beaker. Okay, so now we've added 1 milliliter and the pH is 1.19, so we can put that there. And then we'll add another 1, so we have 2 total. And now the pH is 1.27, and you'll continue to do this until you get to close to the equivalence point. So the equivalence point, because we had 8 milliliters of acid, the equivalence point is going to be when we have 8 milliliters of the 1 molar sodium hydroxide. So that's why when you got close to 8 milliliters, I slowed you down. and said, okay, now do it for only 0.25 milliliters. So I'm going to add the rest very quickly. So I added 2. This will be 3. Whoops. Oh, sorry. So it'll be 3, 4, 5, 6, 7. So at 7, our pH was 2.06. And now we're going to change it and start adding by 0.25 milliliters. And so we'll pour. All right, 2.19. Then we'll pour again, 2.37. Then we'll pour again, 2.67. And then we'll pour again. This will be the 8 milliliter mark. Boom, the pH just shoots up because now we have reached the equivalence point. And you'll notice here the solution is still clear, but I'm going to add another 0.25 now. And look what happens to the color. This is why you want the pure water here to compare the color. Now it is pink, okay? So it can be hard to tell, though, on the background if you don't have the pure water next to it. So then you would note, oh, okay, when I went from 8 to 8.25 milliliters, that's when it turned pink, okay? And note that that's when you get the color change there, okay? So I want you to do this not just for sodium hydroxide and HCl, but also for sodium hydroxide, acetic acid, ammonium hydroxide, HCl, and so forth. Now what I'm going to do real quick, because I kind of messed up, is I'm going to go through, I thought I had fixed all the instances of 1.0 molar, but apparently I had not. So let me make sure I fix that. So this
I had
should,
a question.
yeah, question.
So when it changes colors, that's when we stop recording, right? Just like it was.
No, keep going all the way down. Just note when the color changes.
Oh, okay, okay, okay.
Yeah. So again, it's helpful to have that water right next to it because the color can be hard to see without that.
Okay, so we'll do all the 14.
Yes, go all the way. So you can construct a complete titration curve. So again, your titration curve will look something like what we saw on the slides. At a certain point, the pH will rise up rapidly. I also suggest that when you make a graph, so you can compare them well, make the pH range from 0 to 14, okay? That way you can compare these more directly and see how their shapes are slightly different from one another, depending on whether you're using a weak acid or a strong acid, and so forth, like, or weak acid, weak base, or whatever. Did anyone else want to ask a question about how I did anything there? And I'm just fixing up all the 0.1s to 1.0s. They're all going to be 1.0. I just missed a couple, I guess. And then you'll answer the questions here. Yeah. And so for answering questions 7 and 8, again, it's really helpful if, or particular 8, it's really helpful if you have them all on the same pH scale. So I'm going to show you how you can do that when you make the graph. So first of all, I want to show you, you're going to have all of these, right? But this will always be the same. If you want, you can copy paste this. So you can copy and paste it like this. And insert it. Where is it? Insert copy cells. If you want to just be able to drag and do it like that. Or if you want to plot this as the x-axis, and then, whoops, and then you want for your second graph to be this to be the y-axis. If you hold down Control, you can graph those like that. Okay, so I can drag like this, and if I want, I can click on the top column here. I can right click, and I can copy, and I can insert this again if I just want to do that. That way I can just drag again to graph. Or I can just go like this, and then hold control and go like this. And that will allow me to make the graph of these data points. Remember how to graph from before. You'll go to data, and or you'll go to insert rather. And then you'll go to these little graph icons here. You want this one with all the points, scatter, and choose this right here, scatter. And remember, you're going to want to put axis titles. So this will be like pH. And this would be milliliters of your NaOH or whatever it is, the titrant. It will vary depending on which titration you're doing. And then you could call this, let's say, I chose the second column, so it would be, pH versus milliliters NaOH, titrating acetic acid, something like that. Okay. And again, you're going to want to have your pH ranges all from 0 to 14. That will make it a lot easier for you to see what's going on. So if you double click this, you can get it off of auto here and just tell it, I want 0 to 14. Whoops. 0 to 14. 0. So 0 at the minimum, 14 at the maximum, and there it is. So then I click, and now I get 0 to 14. That way, if you don't do that, you won't notice some of the little differences in the graphs. And then when you go to turn it into me, rather than uploading the Excel file, I think that you should, just to make sure that it comes out nice, if I go to print here, okay, here I'm printing the graph. Also, to make sure that I get everything, you'll want to click on the worksheet here. And if you go to File, Print, you'll see what it will look like. So see here, I can't see this graph. So I may want to, just drag this down here like that, and then put all my graphs down here. And if I keep going down here like that, or put the next one over here, then it will give me nice pages that will be easy to read. Again, if I click on a chart, it will just choose to do that chart. So look at how it's going to print like. And then choose Export and choose PDF, Create PDF. And then you'll do that, and you can save it somewhere. I'll save it on my desktop. And then it will make a PDF for you of this. And then you can upload the PDF. You can also do that to a Word document if you like. You can always print PDF too. So what I'm going to do here for your acids and bases, I thought I had that. Let's see, this is page 1177 to 1181. File. I'm going to save as. What's file print rather. Print. And then you may have to have Adobe PDF installed, or some PDF. Microsoft can print PDF here. Why don't we just do that? And so we'll choose then whatever pages to, if you didn't want everything printed. So I would choose, and this will look different for everybody depending on their printer. So 1176 to 1181. So you can always print to PDF too, but Word has its own function to export to PDF. 151, textbook assets, appendices, Appendix C. KAKB. Appendix C, Ka, Kb, Ksp. So I'm going to upload this right now too, so you have the Kas and the Kbs to refer to. But generally, in this lab, there's not a lot of calculations to do. It's just going through and using the lab software. So at this point, I think we're all done here. So I'm going to let you get started on your lab and let me know if you need anything. I'll also be kind of doing some other things as well, but I'll be here if you need help. Okay. Any other questions you wanted to ask before you start on the lab? I have to also export this too, and I'll export this as a PDF too, and or rather no, I'm just going to save it and I'll upload the new Word document. So the only difference is that I found a couple of places where I forgot to change 0.1 to 1, but all of these concentrations here, they're 1, and so that's why I had to do that. Okay, so. All right, yep, just go ahead and get to it and let me know if you need help. I will update that online version right now. And so it should be corrected, the 1.1s to 1.0. Okay, guys, enjoy your virtual experiment. Have fun. And I will end the recording.